Welcome. In this mini lecture, we're going to cover the first part of Chapter 10, Weak Mathematical Induction. So here, we're going to have an infinite number of statements, S1, S2, S3, that are all true. And this is what we'd like to prove. So to prove this, we're going to show that the first statement is true. We will hypothesize that the kth statement is true, and then we'll show that the kth step implies the k plus first step is also true, and thus every statement must be true. So the key here is to recognize that we're going to show this implication. And the idea is kind of like dominoes. If we've got a series of dominoes set up, and we tap that first one, it makes every domino in the middle fall until it gets to the end. That's what we're kind of doing. So we're showing that we're going to tap the first domino, which, we have to have a first one. But then we're going to show that if we can make the kth domino fall, that means that the k plus first domino also has to fall. And as a result, every domino in our sequence would fall. So let's look at an example. Let's prove that for all natural numbers n, 1 plus 2 plus 3 plus n is equal to n times n plus 1 over 2. So, our proof will proceed by induction. We begin with our basis, and that's we need to show that it holds for n equals 1. So let's actually let n equal 1. Now, we have that 1 is equal to 1 times 1 plus 1 over 2. In fact, that holds, so this statement is true. Note that that 1 is coming from the left-hand side. There's only a single term, and this is coming from the right-hand side. A quick check shows us that that's true, so we have reason to proceed. So, our inductive hypothesis is we're going to suppose that 1 plus 2 plus k is equal to k times k plus 1 over 2 for some k greater than or equal to 1. Now we're ready for our inductive step. The inductive step is where we prove the implication that from the kth term, we can get to the k plus first term. So here, as a note, we want 1 plus 2 plus k plus 1 to equal k plus 1 times k plus 2 over 2. That's what we want. That would be the next statement in our sequence of statements. So, proceeding, now what we're going to do is we're going to start with our 1 plus 2 plus 3 plus k, and to that we're going to add the next term in the sequence. The next term would be k plus 1. And that would be equal to, well, if we first start with this piece here from our inductive hypothesis above, that we know needs to be a k times k plus 1 over 2. And again, we'll add the next term. Now over here, we can continue. We can find a common denominator. So, what do we get? This will give us a 2k plus 2. That's nice because there would be a 2 in there. Or if we think about it as there's a k plus 1 in each, if we can notice that there's a k plus 1 in each of these terms, what we could do is we can factor that out, k plus 1, and then what are we left with in our fractions? K plus 2 over 2. And in fact, that's what we wanted to get. So hence, we can conclude that it follows from mathematical induction that 1 plus 2 plus n is equal to n times n plus 1 over 2 for all natural numbers n. So again, just to reiterate, we started with our inductive hypothesis and we added the next term. And then hopefully we get to where we want, that we would get to the k plus first statement also holding, and that's what we did. So let's look at another one. Now, often in mathematical induction, we start with a natural number, and usually we start with 1, but there's nothing that says that we have to start with the number 1. So we could also start, as we will see, with any other natural number. So we're going to prove that 2 to the n is greater than n cubed for every integer n greater than or equal to 10. So again, our proof, we will proceed by induction. We need to start with our basis. In this case, because we've been told that n is greater than or equal to 10, we're going to choose n to be 10. Then we have that 2 to the 10th is greater than 10 cubed, or in other words, 1024 is greater than 1000, which is true. So our inductive hypothesis will be to suppose 2 to the k is greater than k cubed for some k greater than or equal to 10. So our inductive step now again, let's note, what do we want? It helps us to keep our eye on the prize. So we want 2 to the k plus 1 to be greater than k plus 1 cubed. But this would be equivalent to a k cubed plus 3k squared plus 3k plus 1. So that's just a note to ourselves of where we're trying to get. So now we have 2 to the k is greater than k cubed. Again, starting with our inductive hypothesis. So what would the next term be? Well, we would multiply each side by a 2. That seems to be helpful because this gives us 2 to the k plus 1. But on the right, it's not as obvious where we should go. Well, here's a thought. Rather than having 2 times k cubed, we could have k cubed plus k cubed. That seems reasonable. But that happens to also be k cubed plus a k times a k squared. This seems to maybe be even more helpful, because if we think about where do we want to go, we need something that's going to somehow account for a k squared terms and even a k term. So where can we go from here? Well, that would then have to be greater than or equal to k cubed plus 10k squared. Where does that 10 come from? Well, every k is at least as big as 10. So this k and this 10 now change our inequality to a less than or equal to, moving from this line down to the next line. So we're going to keep going with this process and see if we can't get to where we need to go. So this would be equal to k cubed plus 10k squared. Oh, sorry. That's where we just were. We need this to be equal to our k cubed plus, now I'm going to break that 10 into a 3k squared plus a 7k squared, which in turn, k cubed plus 3k squared plus 7k times k. So again, doing what we did earlier, breaking up that k squared into a k times a k allows us to now hopefully get to where we need to go as far as getting a 3k. So this would be greater than or equal to a k cubed plus a 3k squared plus, well, here at this term, that 7k, k we know is at least 10, so that can become a 70k, which would be greater than or equal to a k cubed plus a 3k squared plus a 3k plus how many extra? 67k, which in turn, this k we know is again at least 10, so this would be greater than or equal to k cubed plus, or less than or equal to, 3k squared plus 3k plus 670, which we know that would be greater than or equal to a k cubed plus a 3k squared plus a 3k plus 1. So again, we can compare just that last term to each other, and we know that this line will definitely be bigger than this line. And what's great about this right here, on the right, this is now exactly where we want it to be. This would be the same as k plus 1 cubed. Thus, we are able to say, again, by mathematical induction, what were we trying to get to? 2 to the n has to be greater than n cubed for all n greater than or equal to 10. And that concludes our proof. So, in mathematical induction at this point, there's a lot of proofs that involve a lot of algebra. And so you're just going to have to watch your algebra and be careful and make sure it's clear what you're doing as you move through each of your steps. That's all for now. Thanks for listening.